Good morning, everyone. Welcome to this session on motion planning and control. My name is Dan Magazzini. I'm chairing this session. Let's start with Louis Dressel on efficient target localization.
So hi, everyone. My name is Louis Dressel. I am a PhD student at Stanford University, and I'm going to talk to you today about decision-theoretic target localization. There are a number of applications where this might be important. I specifically care about localization of radio transmitters. So there are a number of transmitters you might want to find. So there's people buy these small GPS jammers because they're paranoid about people knowing where they are. So they park near airports sometimes, and that messes up GPS systems there. Sometimes you want to find radio tagged wildlife. There are also distress beacons, like avalanche beacons, where you turn these on and you expect someone to come find you. So we can talk about what this problem looks like. You have a X, so a searcher state, which we assume is known. You have a target state, which is typically denoted theta. This is unknown, and I'm also assuming that it's stationary. And a lot of the applications I showed, that's kind of reasonable. If you're buried under an avalanche, you're probably not moving much. A lot of research that deals with radio tagged wildlife typically assumes that the mobile agent is moving faster than the wildlife. And in my case, I'm interested in using UAVs, so that makes sense. So that's why I assume it's stationary. We have a distribution over possible target states. This is just a belief. And our goal is to minimize the uncertainty in this distribution as quickly as possible. So it becomes clear very early on that belief-dependent rewards make sense. So we want rewards or our cost function or our objective function to be defined in terms of the belief and not, say, the state in action. And so this is an example. You have this UAV, and it makes periodic measurements, and the belief is the shaded squares, and we want this to be as small as possible, as quickly as possible, implying we know where the target is. In this example, there's a bearing-only sensing modality, and it's doing a greedy search. So every step it takes the action that it will lead to the smallest expected entropy of the belief at the next step. Right? But greedy methods are typically, generally suboptimal. And here in the planning community, we always ask, how can we solve things optimally? Am I trading any sort of short-term gain for a long-term gain here? And I want a series of actions that will minimize the belief as quickly as possible, not just one step in the future. So when we talk about how to solve things optimally, POM-DPs are the way to go. The problem being, of course, that they're hard to solve. This is your standard POM-DP. You have a state, which is not fully visible. Here the state consists of our known searcher state and our unknown target state. We take an action, and it leads to a new state, S prime, and we receive an observation, which we use to update our belief about the world. And the real problem is that typically the reward here is a function of your state and action. And I'll explain why that's done, but as I said, we really want rewards in terms of belief. So this is your classic Bellman equation applied to POM-DPs, where you can also think about it as where B is your belief state in an MDP. So you have the expectation of the value at future beliefs, the reward at the current belief, and you can express this transition function in terms of the observation and transition function of the MDP. And what is typically done is we replace this rho with B of A as an expectation over some state-dependent reward. And the reason we do that is that this is piecewise linear and convex, and so this ensures that our value function will be piecewise linear and convex. And of course, if you did this out to infinity, it would be truly convex. And so a lot of solvers work by adding these vectors in until you get this approximate value function. So you see the value function is expressed with these alpha vectors, and it's the upper surface. So something that Araya came up with was something called rho POM-DPs. It's pretty simple, but really clever. It's one of those things that you're like, I wish I had thought of that. He just says, well, you can have belief-dependent rewards, but if you just have to make sure that they themselves are piecewise linear and convex. So that was a brief introduction. I'm going to talk a little bit about the methods that I'm going to use to solve this problem, and then I'll talk about some experimental results. So I modified SARSUP. SARSUP is a really good offline POM-DP solver, probably the best, or well, that's like up for debate. And I modified it to have these information-seeking actions, and I called the result Sarisa because, as others have pointed out, making acronyms is like the whole point of being in grad school. Does anyone know what a Sarisa is? Okay. Well, it's a spear that was used by the armies of Alexander the Great to conquer the world. And it was just longer than all the other spears that existed at the time. And apparently, in the ancient world, that was it. Like, you won if you had that. So, at least you can say you learned something in this talk. So I'm going to talk about the reward functions, the backups, and the bounds. All of these things make up this modified version of SARSUP. I'm not going to talk too much about the backups. It's a lot of math, but you can look at that in the paper. So when we talk about reward functions, we want it to be piecewise linear and convex, so we can sort of do the same thing that we do for the value function, which is we can define a set of vectors over belief space. So this is a simple two-state problem. On the left, you're pretty sure you're not in one state, which means you're in the second state. And on the right here, you're pretty sure you're in the second state, so we can represent it. Of course, in higher dimensions, it's much bigger. But the idea is, entropy is a really good measure of uncertainty. Entropy is maximized, so negative entropy is minimized when when the distribution is even, right? Because you don't know much about the world. And so what you can do is you can sort of make this piecewise linear approximation. You can grab all these vectors and sort of store them in this set of alpha vectors. This is actually a pain, right? Because you don't know how many vectors you want to make a good approximation. And so what people have done is they've found other things. So the most common example is the max norm. So that's just the state with the maximal density in the belief, right? And it turns out that you can represent that really easily. Like, you just have one vector per state, right? So we can represent this. These are the standard basis vectors, right? That are 0 everywhere and 1 in one of the particular dimensions. So that's really convenient. The problem is that sometimes there's like too much reward given here, and our goal is really to get to a very concentrated belief quickly. So we might use something like a threshold reward, where we have this, we only start giving rewards after some value of probability. And then there's another option, which is this guess reward, which is very similar to the max norm, but we only give a reward once we've committed a guess action. So once we take this guess action, then it takes this the maximum value. And the idea here is that the UAV or the agent will reason about when to stop gathering information. So it'll move as quickly as it can. It doesn't get any reward until it starts getting to a belief where it's confident that it can start getting a good reward. So this has been proposed before. These two have been proposed in the context of Hamdi Peas with information rewards. And all I've done is just sort of port them over to this row Hamdi P formulation. So I'll actually go back. So I skipped the part about the backup. What's really nice about these reward functions is that you can represent them with a relatively small set of alpha vectors. You can also do this with this guy. I didn't do it here. But what I show in the paper is that you can also do the backup, which is like a core inner loop of Hamdi P solvers, without even like referring to this. So you don't even have to do this sort of maximizing over all the vectors. But that's in the paper if you want to look at it. So when you start looking at the lower bound, so a lot of approximate methods, they have an upper bound and a lower bound. And the idea is you sort of squeeze them together until you have a pretty good approximate solution. And it turns out that with this formulation, the lower bound is atrocious. And it's atrocious because to make it a good lower bound, you want to have some like a worst case scenario, kind of. And the worst case scenario, like the belief is like fully, it's uniform, so you end up getting a very low reward. But in our problem, what if we know the belief will be constant? That is, it doesn't change. Then we know that the max norm of the belief will also not change. And then we can say that at a given belief, if that max norm is constant, we can just discount it to infinity, right? So that'll look something like this, right? So at some belief, the max norm, and just discount it. And it turns out that this is a linear function of the belief. I've assumed a stationary target, so that means in each step I don't have to worry about the belief getting diffuse because the target is moving around. And we just need a non-observing action. Or more specifically, we need an action about which the observation from which the resulting observation is like deterministic, right? So if that's the case, if I take an action and I know what observation I'm going to receive, then that doesn't change the belief at all. That hasn't given me any information. And if we do this, then we can be sure that the belief will not change, right, when we take it. And it turns out when we use that guess reward action, that guess action is sort of this non-observing action, right? It doesn't return an observation, and then you know the belief is going to stay the same. And so if we look again at our two-state problem, this is the original lower bound, this is the upper bound, this might be what the actual value looks like, and this is what this improved bound looks like. And you see that makes a huge difference in terms of like having to solve all the way up. Another method that I looked at is DP Lite. So that's an online method, as opposed to Sarisa, which was an offline method. And this is another thing that's kind of clever, and you're like, I wish I had thought of that. Basically, they just solve an MDP at each step, and anything they don't know, you take an expectation over. So in this case, this is your original transition function. Remember, your state is just your known state and your unknown state, but you don't know what the value of theta is, so you just take an expectation over it. And then you have the same thing for the reward, but they add this exploration reward. And the idea behind that is that your value tends to be highest at the corners of the belief simplex. So if you encourage exploration, that'll be good. And so that's really nice for me because I'm interested in belief-dependent rewards. Okay, so now I'll show the results. Okay, got it. So I'll show the results of some experiments. I came up with a toy problem because this is Hamdi Peas, so that's pretty common. And I also I work with in like the controls community and the aerospace community, and they're always like, why don't you just use like a greedy method? Like it works well. And I kind of wanted an example where this is not the case. So you have this UAV, and it makes range measurements of this target, right? And this is the belief. It doesn't know where it is, and it can climb above the buildings, but that takes 2 steps. Or it can start moving through the buildings, and it receives like a noisy measurement. And the idea is that a greedy method won't be able to know to take the step that's, because here you don't make an observation, you're still moving up. And so I actually solved this, and it shows, hey, the 2 information gathering methods take the right action. And when you use SARSUP with a surrogate reward, so a surrogate reward is a state-dependent reward that sort of mimics a belief-dependent reward. So here the surrogate reward is, I want you to sit over the top of this transmitter, right? And the idea is that in order to do that, it has to find out where the transmitter is. But of course, it gets pulled towards the direction of the transmitter because it wants to be close to it. So it ends up doing the bad action. Right. Okay, and when you look at this, this is just showing, we got it takes less time to localize. And the solve time with this Sarisa is like 0.06 seconds. That's with the improved bounds. And you can see it only required 237 backups. When we do the unimproved bounds, it takes like 17 times as long, and there are many more backups. So it's just showing the importance of that. Another experimental problem is rock diagnosis. So this is very similar to the rock sample problem. Every rock is either good or bad, and in rock sample, the goal is to sample the good rocks. In rock diagnosis, the goal is only to determine if the rocks are good or bad. So you take measurements, and these measurements are noisier the farther away you are. So we then solved and evaluated by the max norm. And it turns out this surrogate method is simply the original rock sample policy, right? Because if you go to sample the good rocks, you need to learn which rocks are good and which ones aren't. So there are a couple things. Number one is this guy gets the max reward, which makes sense because this is what he was trained on. And kind of disappointing, it takes forever. It didn't converge. I just cut it off after 2 hours. I said, you're done. Whereas the surrogate reward solved a lot quicker. So there's still a problem with computation that I'll talk a little bit about later. I evaluated with the threshold reward, and you see that even when you solve with the right reward, DP Lite does better. And I think this is because, again, this DP Lite is encouraging you to the corners of the belief simplex. And so the bounds aren't good enough. Still, you can see the value of the improved lower bound. After about 10 seconds of solving, it's better than like 2 hours of solving without it. It's a big deal. And this is the average steps to a very concentrated belief. You can see DP Lite's pretty good. The threshold method, even with solving not too long, does a little bit better. And the max norm, it takes longer to get there. So I implemented this on a very simple jammer hunting problem. We hunted this Wi-Fi router, And the search area was very simple. It's just an 11 by 11 grid where each cell is 10 meters by 10 meters. The state is the cell the UAV is in, the cell the jammer is in, and the actions are you can move to an adjacent cell, you can rotate and make a bearing measurement, or you can sort of hover, which ends the mission, and that's kind of like your guess action. So I discretized the observation space, and then I had this belief-dependent reward, right, where it's 1, or it's the max norm if I'm hovering, and there's like a cost to moving. And I defined a surrogate reward that's very similar. This is a state-dependent reward where you get 1 if you're hovering over the jammer, right? So that's the idea behind that. And so when you solve these things, it does seem like the belief-dependent reward, the Sarisa, does do a little better. The difference is like very slight versus like a greedy method. And it's possible that for this problem, the greedy method just happens to be really good. I think the more interesting thing is at this point out here is what the unimproved bounds look like. So that's definitely Pareto dominated. And if you consider the bounds, so I think this is really interesting. So this unimproved bound is like pretty terrible. This Sarisa is okay, but it's very similar to the surrogate reward. And remember that surrogate reward is still trying to solve the problem of finding it, right? And so I think there's something just like inherently difficult about this that's not necessarily a problem with sort of these bounds that I've necessarily given. It's just the problem is difficult. And I think that merits further investigation. So, very quick video. I'll be done in a sec. Am I running out of time? 10 seconds. Well, okay, we'll be close. So this is what it looks like. These are like actual flight test results. It rotates in place, right, and then it gets some belief. And so this is a small problem, of course. And the goal in my future research is to scale up. And so you see it moves to a new place, and then it rotates, and then it updates the belief. I'm going to go ahead and just, we'll let it go one more step. Okay, so rotating takes a long time. Okay, and then, the belief updates. This will be like 10 seconds. So the idea here is, it rotates in place. Here's a video of it doing it. So it rotates in place, and then it moves to another place. And the idea behind this is that, okay, this problem is very simple, but we're starting to get to the point where we can compete with these greedy methods and implement it on real systems. So the conclusion is that we improved these offline solvers. We implemented it on a real robotic system. DP Lite tends to work well. Future work is all going to be about scaling up the work. So this is improving the bounds, especially that upper bound. Applying it to new sensing modalities. So this is a more interesting problem where you're taking measurements all the time instead of this move and rotate. And so I think maybe that'll be a case where the difference between a greedy method and these sort of optimal methods is more clear. So that's all I got.
We are very late. Perhaps one quick question while the next speaker set up. Is there a quick question? I have one. There has been a bunch of work on using planning for search and track to maximize the probabilities of spotting the target. Do you compare with those?
My problem, there's no searching part because you can always detect the target. So, I'm not sure what work specifically you're... Okay, that'd be great.
Okay, let's thank again the speaker.
Oh, right.